So we have constructed this kind of 100 square meter light receiving area. STA value was about 0.8%, and then that about 300 liter per hour is the optimum value of gas evolution, and it is enough to test our gas separation membrane. But we need to do the one more very important thing is this one, verification of safety total system operation, because that's our system involves hydrogen and oxygen mixture. Actually, we have been carrying out this system for more than 3 years, but we have never observed any spontaneous explosion of this system. So that's such a kind of spontaneous explosion is very rare case. Nevertheless, we need to examine that by causing intentional explosion at the various point of this system. Then that we have to verify that this kind of system will not be destroyed or damaged. And here I just show you two typical experiments of such kind of experiment. In this case, we use polyvinyl tubes. Inner diameter is 10 millimeter, and the total length here is 100 meter. And inside of this tube is filled with 1 bar of hydrogen and oxygen mixture in 2:1 ratio. And here we have a spark plug to cause the explosion. And this is a real-time experiment, so that the explosion takes place instantaneously like this one. But as you see here, there is no damage of the these tubes. And this is exactly the same experiment, but it's 280 times slow motion. So you can follow that how that explosion proceeds like this one. So from this video, we can evaluate that this explosion proceeds about 2,800 meters per second. That is much faster than the velocity of sound. So it is a so-called detonation. However, we observed almost no damage. We can carry out the same experiment many times. And maybe some of you are afraid that the gas separation membrane might be destroyed by this kind of explosion. And actually, in this case, that this membrane is working, and then we cause explosion intentionally through this line, like this one. Okay, and this is we have made a window to see the inside of this gas separation membrane, and now you can see the inside of this one, like this one. But as you see here, that there seems to be no damage, and actually we observed no damage or performance degradation of the membrane after several explosion or detonation experiments. That means that if we design suitably, we can avoid any damage of the explosion if it will take place. Now let me move to the a little bit different type of systems. This scheme, photocatalyst sheet. In this case, we use two different types of photocatalyst. And then I will talk about this one, and so that is a so-called Z-scheme water splitting system. This is lanthanum rhodium co-doped strontium titanate for hydrogen evolution. This is molybdenum doped bismuth vanillate for O2 evolution. The color is a little bit different, but if we observe by UV with diffuse reflectance spectroscopy, the absorption edge in both cases is extended to about 520 nanometers. Then the preparation procedure is shown here. We mix these two particles in an isopropanol solution, then just drop casting on a glass plate. Then after drying, we can get this kind of mixed particle layers. The thickness is at most about 10 micrometers. Then after that, we deposit a conducting layer, in this case, a gold or carbon by sputtering or evaporation. Then after annealing to fix this layer to this photocatalyst particles, we put another glass plate. In this case, this glass plate contains double-sided carbon scotch tape. So if we push and then peeling off, we can get this kind of structure. There still remains some physically adsorbed particles. So after ultrasonication to remove such a physically adsorbed particles, we can get this kind of photocatalyst sheet prepared on a glass plate. And if we look at this surface, by SEM, as you see here, the structure is not really so sophisticated. And this is red dot indicates the oxygen evolution photocatalyst. This green dot indicates the hydrogen evolution photocatalyst. And this blue dot indicates a contact layer, in this case, a gold. that this is a total feature of this photocatalyst sheet. But nevertheless, if we put this photocatalyst sheet, in this particular case, we use a carbon as a contact layer, and then irradiated by a solar simulator, we can get this kind of bubble is coming out. This is a bubbles of hydrogen and oxygen, which is evolving from pure water without any electrolyte like this one. And the quantum efficiency at 420 nanometer was about 33%, and solar to hydrogen energy conversion efficiency in this particular case was about 1.2%. And now let me summarize my talk. Here I show our image to install this new technology into the real world in the near future. We like to make one unit of this system to 10,000 square meter or 1 hectare. That is 100 times wider area than our prototype system that I showed in the previous slide. And in this area, we have only one gas separation unit. And at the very beginning stage, we like to achieve about 5% solar to hydrogen energy conversion efficiency. This is a value that our collaborated industry people evaluated that to make a commercialize this new technology, we need at least 5%. So the question is that, is it really possible to achieve such numbers? Here I show that the photocatalysts, which are able to split water into hydrogen and oxygen. This circle shows the one-step overall water splitting reaction. This triangle shows the two-step overall water splitting reaction. And this axis is apparent quantum yield in a logarithmic scale. And this is the absorption edge of the photocatalyst. And this is the data of about more than 10 years ago, before our UpChem project starts. Our UpChem project is a 10-year project. And after this UpChem project, we increased the photocatalysts, which are possible to split water. This is a one-step over water splitting reaction. As I showed previously, that now this number is almost 100%. And also we developed two-step over water splitting systems like this one. However, to achieve the STH value of 5%, we have to get into this region. Okay, at present, we have not yet get into this region. To reach this region, probably we need to improve the efficiency of these materials. I mean that the absorption edge is located at about 600 nanometer or even longer. So the question is that, is it really possible to get into this region? Now let me just use this oxysulfide materials as an example. If we like to achieve the SH value of 5%, we need to achieve about 30% of apparent quantum yield. If we like to achieve 10%, we need beyond 50% AQY. And is it really possible to achieve these numbers? Here I show that very simple calculation. The band gap energy of these materials is 1.93 eV. And to thermodynamically split water into hydrogen and oxygen, it takes about 1.23 eV. So the remaining energy is 0.7 eV or 68 kilojoules per mole. This is actually the driving force that we can use to improve the AQY or rate of water splitting reaction. And we believe that this value is enough to improve our system to this region. So we are now focusing our effort to achieve these values in the near future, hopefully in a few years. Now, acknowledgement. Professor Kudo at Tokyo University of Science and Professor Sakata at Yamaguchi University, they are our long collaborators. And here I show that some of my co-workers' name who contributed considerably to my talk today. Especially, I like to thank to Professor Takata. He developed a highly efficient aluminum doped strontium titanate. And Dr. Wan Chen, she developed the Z-scheme over water splitting photocatalyst sheet. And Dr. Nishiyama and Dr. Yamada, they are in charge of the construction of the total solar hydrogen production system. And the most part of my talk was the result of this UpChem project. This is a national project supported by NEDO. NEDO is a funding agency of MITI, Ministry of Economy, Trade and Industry. And this project was actually finished last February. And right after that, from last March, we started the second phase of UpChem project. And then the purpose is to construct a practical solar hydrogen production system that I showed in my previous slide. Thank you very much for your kind attention. Hello?
Hello, sir. Thank you for enlightening us. Sir, we have some questions.
Okay.
Sir, first question is, what is the thickness of the photocatalyst sheet that you have used? And how does the thickness affect the hydrogen evolution reaction?
Okay. Can you see my slides at present? No.
No, sir. No, not right now, sir. You have to reshare it.
Just wait a minute. Okay. Now. Can you see my slide right now?
Yes, sir.
Okay. Okay. In the case of one-step over water splitting system, as I showed here, that this is 10 micrometer. Okay. Then this is the photocatalyst layer. So less than 10 micrometer thickness. Okay. And we also tried to make a thinner or thicker layers, but 10 micrometer is enough to get the optimum activity of this in this case. And in the case of the this scheme water splitting system, this one, in this case, it is also less than 10 micrometer. Okay, yeah, several micrometers thickness. But I should say that in this case, if we can make more well-ordered structure, probably that activity or quantum yield will be improved more. At present, our quantum yield was about 30%. Okay, so to get 50% or 70% quantum yield, we need to make a more well-ordered photocatalyst sheet. Okay.
Thank you, sir. Sir, the next question is, what type of material can be used for the production of the membranes for the separation?
Pardon, could you say again?
Sir, what type of materials can be used for making the membranes for the separation?
Membrane.
Yes, sir.
What kind of membrane?
Sir, for the membrane for the separation of that hydrogen and oxygen.
Okay, we are now using organic membrane that is made of polyimide membrane. At present, we are also developing polyamide membrane that is developing by a Toray company. The Toray company is one of the biggest company of the desalination of seawater. And then that is more or less similar that one. So that is also possible to separate hydrogen from water. And we are also developing inorganic membrane that is a zeolite membrane. It is actually being developed by Mitsubishi Chemicals. But in the case of inorganic membrane, we need to introduce a dry hydrogen and oxygen mixture. If there exists a water vapor together, the zeolite pore is filled with water vapor, water molecules, so that the separation efficiency becomes much worse. So we consider that probably that organic membrane seems to be more suitable to separate the wet hydrogen and oxygen mixture. Is it okay?
Yes, sir. Sir, the third question is, could you
Yes.
please comment on the differences for the efficiencies of photocatalytic, photoelectrocatalytic, and electrocatalytic water splitting?
You mean that the difference of the efficiency of photoelectrocatalytic and photocatalytic method?
Yeah, sir. Yeah, exactly, sir.
Okay. Okay, very frankly speaking, that if you use the tandem system in combination with the photovoltaics and the transparent photoelectrochemistry, then the best one is now already about 30% or something like that. If you will not use photovoltaics tandem system to photoelectrode system, it is about 10%. We have already achieved such numbers. But in the case of the particulate photocatalyst, it is about 1.2 to 1.3%. So that at present it's a much higher efficiency is obtained if we use photovoltaics and photoanode or photocathode materials. However, the cost to extend to wide area, as I showed that we like to extend this kind of system to square kilometers or several tens square kilometers. In that case, we try to extend such a wide area. We have never succeeded by using photoelectrochemical system. And in the case of the photovoltaics and electrolyzer system, the combination is not really so good because there exist several very complicated systems to connect the photovoltaics and electrolyzer system. Then that's the produced hydrogen cost becomes much more expensive than that's produced from the fossil resources. So that's why that we are now developing this kind of system. As I said, by this type of particulate photocatalyst system, if we can achieve 5%, we can that's the cost becomes much lower. So that's why we are working on this kind of system. Okay.
Thank you, sir. So the next question is, what could be the differences in terms of doping for the metal and non-metallic doping?
You mean the metal and non-metallic doping? Okay. As I said that in my, can you see this? Can you see this slide?
Yes, sir, it's visible, sir.
Yeah. And actually, that's in the case of strontium titanate, this material is originally N-type structure, N-type material. So that if we dope lower valent cations, that is a P-type doping. In this case, the sodium plus or gallium 3 plus. This is a lower valency from the strontium 2 plus or titanium 4 plus. In this case, that we can reduce the N-type character. If that N-type character is too strong, then if we put these particles in an aqueous solution, the band bending becomes very sharp at the interface. That means that the photoexcited electrons is difficult to migrate to the surface. That's why that if we dope the P-type doping, then such kind of barrier becomes low. That is much easier to extract photoexcited electrons and as well as holes to the surface to react with water molecules. Is it okay?
Yes, sir, it's okay, sir. So the next question is, sir, other than doping or sensitization, what could be the other strategies to improve the efficiency?
Doping and could you say it again?
Yes, sir, please. Sir, actually, she's asking that other than doping or sensitization, what could be the other factors that can improve the hydrogen production efficiency?
Other factor okay. Okay, in the case of the Z-scheme water splitting reaction and the Professor Kudo's system, he actually, okay. This is, you can see this photograph, right? So in this case, rhodium doping is important. This rhodium actually gives visible light responsibility. So that if we dope this rhodium 3 plus cations into strontium titanate, we have some activity in visible light region. So that in that case, that we can improve the efficiency and the visible light irradiation. So that this kind of doping, in some cases, very effective. However, that this kind of metallic doping, I mean that containing element, d electron containing element, the rhodium 3 plus contains some d electrons. If we dope such kind of metals, lot of amount of lot amount of rhodium, the activity decrease again. So the amount of dopant is very important to get good activity. Is it okay?
Thank you. Yes, sir. Thank you, sir. And sir, the last question is how the glass window will be suitable for an UV active photocatalyst like strontium titanate. Sir, are you using any kind of specialized frosted glass or any float glass that can be used?
Okay, the window glass. In this particular experiment, we used the window, which is also used for the photovoltaics, the same one. However, we consider that when we develop a visible light responsive photocatalyst, we don't need to utilize so expensive glass. I think that to construct a water splitting panel, maybe we need to develop a special type of, I mean, the lower cost of the materials to make a window of the water splitting panel. We are now searching such a kind of materials. Okay.
Thank you, sir. And sir, the one last question. It's
yes.
Can you just go for a very cheap material like the graphitic carbon nitride instead of these costly elements?
You are talking about the carbon nitride.
Yes, sir. Yes, sir. Can you just go for that?
Carbon nitride is also very interesting material, but it is a little bit difficult to split water into hydrogen and oxygen, although that's Professor Shin-Chun Wan's group achieved such a kind of activity. Maybe I think that the carbon nitride is a very, very good materials, but it is better to combine with for the Z-scheme water splitting reaction with some other materials, some other photocatalyst. Yes, but it is very promising materials. Yes.
Okay, sir. Thank you, sir. Thank you so much for answering all the questions.
Yes. So now.
So, sir, there are no more questions right now. Sir, if we have more questions, we can write to you directly with your email.
Sure. Yeah.
Okay, sir. Okay, sir. Thank you. Thank you so much, sir.
Okay. Thank you very much. And then. Is it okay?
Yes, sir.
Now, it is my immense pleasure to invite Professor Uday Narayan Maiti for the next talk session. Professor Uday Narayan Maiti is a professor at IIT Guwahati in the Department of Physics. He has submitted his doctorate in the year 2010 from Jadavpur University, followed by postdoctoral until 2013 from Korea Advanced Institute of Science and Technology, South Korea. His research interests include, but not limited to, carbon-based nanomaterial, graphene oxide, carbon nanotube for energy storage, conversion, and catalysis. The title of his talk for today is Controlled Microscopic Assembly of Nanomaterials for High-Performance Energy Storage Applications. Participants are requested to mute their mic and they may put their questions in the chat box, comment section, which will be answered at the end of the tutorial. I will now request Professor Uday Narayan Maiti to please gather the session. Over to you, sir.
Thank you very much for your kind introduction. Let me share my screen. So, just a moment. Can you see my screen?
Yes, sir, it's visible.
So presentation is visible to you, I guess.
Yes, sir.
So good morning, everyone. Today I'm going to present my work on controlled macroscopic assembly of nanomaterials for high performance energy storage application. As has already been introduced, that I belongs to Department of Physics and also I am associated with the Center of Nanotechnology, IIT Guwahati. So the layout of my presentation is as follows. First, I shall introduce some energy storage technologies and why the energy storage is important. Then I shall introduce that how nanomaterials can boost the energy storage performance and what are the available nanomaterials which are most important for the energy storage application. And then I shall introduce that how to construct the energy storage devices and what are the current existing challenges. Then I shall introduce the main focus of my topic is the how the macroscopic assembly of tiny nanomaterials in the form of some porous hydrogel can address the existing challenges. And in this connection, I shall introduce several different types of hydrogels and their merits and demerits, and then how those hydrogels boosted the energy storage performance as compared to the current existing state of art. So but the question is that why we are talking about the energy storage, why it is so important. As you know that due to rapid depletion of the fossil fuel, people are going towards the renewable energy, like converting solar energy into electricity or wind energy into electricity. However, those the renewable resources are intermittent in nature. You cannot have the sun in the night or you cannot blow the wind on demand. So whatever the energy converted during the daytime or whenever the wind is there, you have to store it efficiently so that you can use it on demand and during the night time or whether there is a peak requirement. So always if you seen any of the solar cell, always there is a energy backup. You can see there is a battery connected to it. It is mandatory requirement, the secondary of any of the renewable energy system. Not only the renewable energy technologies, but if you go to the portable electronics, which are mainly used offline, I mean, you cannot use always with the connecting with the electrical connections. So in these portable electronics, you need battery, and you know that we are already using the battery, and we need always more and more energy storage for these portable devices so that we can use it for the long run with a single charging. And after that, the current focus is on these vehicles, the I mean charging vehicles, where it is the battery operated and it's actually zero carbon dioxide emission. They actually are the more green technology. So right now the electrical vehicles are already in the market. So for that also we need the efficient energy storage. Going into the how to construct the energy storage devices, let me give you an idea that what are the figure of merits for energy storage devices, how we could judge that this energy storage device is better as compared to the other one. Of course, the most important part is the energy. I mean, how much it can store the energy. More energy is always is the better. And if you compare the energy of a smaller device and a bigger device, definitely bigger device has a higher storage. But so how to compare that whether which particular one is more efficient, then you have to give the normalized energy, that is the energy density, that per kilogram of the material how much it can store the energy, and it is generally represented as the watt hour per kg, or this is known as the gravimetric energy density. And also we require the volumetric energy density per unit volume, per unit liter, how much of energy it can store. This is also very important because whenever you would like to put a energy storage devices within a small space, you want that energy is concentrated within a very small space, so that you need the high volumetric energy density. And not only that, this is another important metric. This is the areal energy density. How much of energy is there for a device per unit area? Because you want, suppose I am having a 10 centimeter square by 10 centimeter square a energy storage device. within this device how much energy it can store. So these are the figure of merits. So this is the specific energy density, either gravimetric, volumetric, or areal energy density. And another more important aspect is the power density. Power density can be understood from this particular picture. You see that there are a lot of water here. That means it has a lot of storage, but it cannot give you the water at a very faster rate. But this one has a less amount of water, but it can give you the water at a very faster rate. That means whenever we need energy at a very faster rate, suppose the car is accelerating, okay, so in those cases, or it is during the braking, you need lot of energy within a short period of time. So for that you need lot of energy per unit time. This is known as the power. So again, the power can be gravimetric, volumetric, or areal. And beyond this energy and the power density, there are other two metrics like life cycle. How many times you can charge and discharge the energy storage devices before discarding the same. So if we can use it for long run, suppose we can charge and discharge for thousands of times, that is always better. So the life cycle, higher life cycle is always better. And the charging time, that how fast the device can be charged, because we always want, whenever we are using the mobile, that if it is possible that we can charge it within 1 minute or 2 minutes, it is always better. So the charging time is also a factor. So in this connection, so what are the available technologies for the energy storage? I'm going to introduce two most important electrochemical energy storage technologies. One is the battery and one is the supercapacitor. So batteries, they have a very high energy density, as you can see from this comparison chart, but their power is very low. They cannot be used to supply the energy at a very faster rate. However, the supercapacitors, their energy is much lower than the battery, but this power is very low. So whenever you consider for the high power application, the supercapacitor is always preferable. But however, the distinction between the battery and supercapacitor right now are not so so different, because right now the energy density of supercapacitor also approaches towards the battery. So we need for any energy storage devices as much energy it can store, and its high power is also better. High power is also better. And if you compare the life cycle, the battery generally it can be charged and discharged 500 times or 1000 times. However, the supercapacitor can be charged to 15,000 times or more. And charging time, it generally takes hours for the battery. However, for the supercapacitor, it takes minutes to seconds. The environmental risk, battery contains a lot of hazardous chemical, and lithium is also there. So environmental risk is always an issue. However, for supercapacitor, it mostly use the non-inflammable and the aqueous-based system, so it is much safer. And from this chart also, as I mentioned, the quantitatively you can see that the battery has much a higher energy density here. However, its power is less. On the other hand, if you consider the electrochemical supercapacitor, it has a huge power, okay, some orders of magnitude higher than the battery, but its energy density is lesser than the battery. But there are certain regions where there is an overlap. The battery and the supercapacitor, they have a similar energy density. So they are, as I mentioned, they are approaching. The difference is not right now. It's not so distinct. If I compare that how this out of these two technologies, my main focus will be supercapacitive energy technologies, because this is more safe, and this can store much faster energy, and it can give very high power. So the question is that how a supercapacitor store the energy. Now I can start with the very basic of the dielectric capacitor, which we studied in our school days. That for a dielectric capacitor, capacitance is equal to epsilon A by D, where this epsilon is the permittivity of this dielectric media, and D is its thickness, and area is the area of this electrode. So in this case, the energy of this dielectric capacitor is equal to half CV square. Now suppose if I remove this dielectric with some electrolyte, so this dielectric is removed over here, we put these two electrodes within some solution. For example, you put it in water solution, having some sulfuric, having either the alkaline media or the acidic media. Suppose sulfuric acid is there. So once you put them within this aqueous media, it's either acidic or alkaline media, then what happens, for example, for sulfuric acid? So sulfuric acid, you have H plus ion and SO4 minus ions. So when you connect with the battery during the charging, so the minus charges, minus ions, that means the sulfate ions, go towards the positive plate, and the positive ions, that means the H plus ion, go towards the negative plate because of this, because you have connected with this battery. So as a result, right now you can see, if you compare between these two, the one of the, let me just use my laser pointer. Yeah, if you see here that there is a one electrode and there are some negative charges and they are separated by the water molecules, the solvent molecules around. So this one, isn't it the one segment, this segment, it looks similar to the dielectric capacitor, where there is a positive charge separated by a dielectric and negative charge. Here also it is positive charge, negative charge, and separated by a dielectric, where the dielectric is the water molecule. As a result, right now, if you check this formula, that C is equal to, hello? I'm getting some noise from there. Anyway, so if I check this one, any of the electrode, you see that this is a positive charges and there are some negative charges. They are separated by a dielectric. This is very similar to a dielectric capacitor, where capacitance is epsilon A by D. Right now, D is the diameter of the water molecule. So as you can see that because diameter of the water molecule is very less, so that's why you can get a very high capacity. Like C will be very high. So this one, this electrochemical capacitor, these are known as the supercapacitors because their capacitance is very high. But the important thing is here, right now, instead of one capacitor, you are having the two capacitors. One on this side, one is anode side and one is cathode side. So that you are having the two capacitors and they are connected in series, so that the overall capacitance is equal to the just the series combination of two capacitors. So it's a C1 of one and C2 of another one, C1, C2 by C1 plus C2. So by this way, you can increase the capacitance to a significant amount. This is a very high amount, orders of magnitude higher than the dielectric capacitors. And there is another form of the supercapacitor. This is known as the pseudo capacitor. This is the working mechanism is very similar to this one. This is known as the electrical double layer capacitors. The name came from the case that here you see that positive and the negative charges happens. There is a double layer formation. Okay, double layer of the double positive and negative charge happens. It's the electrical double layer formation happens. So it is the EDLC type capacitor. And the pseudo capacitor is also a supercapacitor, but here the mechanism is a bit different. The same thing happens, like negative charge goes towards the positive plate, positive charge goes to the negative plate, that additionally there is a charge injection from these ions to the electrode. In this case, there is no charge injection. This is just the adsorption of ions. There is no charge transfer between the ions and the electrodes. However, there is additional charge transfer between the ions and the electrodes. As a result, those pseudo capacitive materials, their storage performance, their energy storage performance is higher than the electrical double layer type. However, they are much slower. So because the main advantage of the supercapacitor is they can be charged at a very faster rate, but these pseudo capacitors, because of this reaction is happening at the surface, they actually they are much slower than the EDLC type. Now depending on whether we want very fast charging one, then we should go for the electrical double layer type. But if we want that the higher energy density is the more, the requirement is for higher energy density, we'll go for the pseudo capacitor. So now the question is that, we already know that what the mechanism by which energy storage happens. Now the question is that how to increase the energy storage performance in a supercapacitor. What should be the material characteristics used in the two electrodes so that we can enhance, we can boost the energy storage metric. So for this one, here is one of the schematic example, which you can see that instead of this a thin plate, if you use instead of thin plate, if you use a porous electrode where you are having some thin sheets of some materials, so this adsorption of charges not only happens in two-dimensional surfaces of this electrode, but on the each and every surfaces of these porous structures, so that you can increase the energy storage to a high extent. Because again, I can refer to this formula, C is equal to epsilon A by D. If you can increase this A, the area, then you can increase this capacitance, and as a result, you can increase the energy density. In these connections, one example I have given over here, these are the some sheets of graphene, which I am going to also introduce. And if you, instead of having a solid some electrode, if you are having the several nano sheets of graphene, so the electrolyte ions can store over each and the individual surfaces. So as a result, you can increase the energy density to a larger amount. So I just introduced the graphene. This is one of the important material for the energy storage. But what the graphene is, let me just give you a brief introduction. So graphene is nothing but a single layer of graphite. These are the graphite we used to use for the pencil or other stuffs. And if you look at the construction of the graphite, it contains the several individual layers of single layers of carbon. These individual layers are known as the graphene, and they can be separated by simple scotch tape method. You put on some tape and you do the scotch taping several times. You can separate it, and the importance of these materials is that they have a very high surface area. Per unit gram of these graphene, the surface area is 2,630 meters square. That means with 1 gram of graphene, you can cover nearly 1 football ground. And it has a very high conductivity, that is up to 10 to the power 6 Siemens per centimeter, and it is chemically inert, so it is more stable form. Now, when it comes to the energy storage devices, this scotch tape method is not adequate method, because we need kilograms of this graphene. So for that, people used to use, this is the most convenient strategy. It started from graphite powder, then the oxidation, then it undergoes oxidation. Because of the oxidation, some functional group attached over each and the individual layers of the graphene. So as a result of these functional groups, the distance between two layers increases, so their van der Waals interaction decreases. And if you just shake it or make some sonication, they exfoliate into individual layers. These are known as the graphene oxide, because it is not graphene, because there are certain functional groups attached over the surface. And now by some chemical or thermal reduction method, we can strip off those functional groups to great extent to get the chemically transformed graphene, also known as the reduced graphene oxide. So in this process, we can get the kilograms of the sample of the graphene. And there are other materials also for these energy storage devices, like some conducting polymers like polyaniline. So in the polyaniline, they also do some redox reaction, the Faradic reaction, the oxidation and reduction. So their main mechanism is the pseudo-capacitive type, as I already introduced. And for the polyaniline, you can use some nanowires form to maximize the surface area. And there is another new entry in this field. This is known as the magazine, where this magazine is the main material is the max phase, where there are some carbide layers of titanium, vanadium, other carbide layers. Those carbide layers are connected by aluminum. Now, if this interlayer aluminum is selectively etched, it leads to this layered structure like a clay-like structures, and they can be exfoliated like a graphene exfoliation. They can be separated individual layers. Here I have given you one of the example of the magazine is a titanium carbide based, the Ti3C2 and Tx. The Tx denotes that during this exfoliation and this chemical treatment, there are certain functional groups like OH and COOH functional group attached over the surface, and this gives rise to the water dispersibility of those magazine nanosheets. So the story will be based on the graphene polyaniline in a magazine here. And let me then show you that how to construct. Suppose the material is available with us, how to construct the energy storage devices. So for construction of the energy storage devices, it is very simple to construct. So there are two metal current collectors. Here is one metal current collector. Here is another metal current collector. And on each and every metal current collector, you put your materials, and then they are separated by a separator. This separator is the insulating separator, but they are porous so that ion can transport through this separator. And it also, this insulating separator avoids any direct electrical contacts between the two electrodes. Now question is that how to construct one electrode, how to put your material on this metal collector. So the industrially, or the most common method of putting the material over this current collector is some printing. Okay, so in this printing, the material, suppose graphene or magazine or polyaniline, they first mixed with some binder. These are binder, means these are like a glue. The Nafion, PDBA, PTFE, these are the glue. They just mix it so that you having some mold kind of things. So this mold you cast over this metal plate, and then you construct this device. So this is the common method industrially used, and this is the most commonly used method. However, there are certain issues with this particular method, because these binders, they are low conductive additives. They are mainly of insulating nature, and during this process there is a lot of aggregation of these graphene or magazine sheets, so that their surface area cannot be accessed. It's a very compact arrangement. And there are other methods where you can completely remove the additives, because it is necessary. If you can remove the additives, then conductivity definitely will be better. So for that, there are some other alternatives like filtration and the spray coating technique. So in the filtration and the spray coating technique, you start with some dispersion of these nanosheets, and you either spray coat over the substrate or do filtration to get the film. But in this case, although this is a binder free sample, so there is no problem from the insulating binders. But in this case, those sheets are very compactly arranged, as you can see from the cross-sectional ACM image. So whenever the electrolyte ions wants to seed, they can seed mostly on the outer surfaces. They cannot go inside. But our main target was to use nanomaterials to access the surfaces. But due to this restacking, we cannot access the intermediate layers. So the main purpose of using the nanomaterials gone here. So in this case, what could be the best possible scenario? Best possible scenario could be this one. You assemble the nanomaterials in a form that it is some freestanding structure, having no additives of the insulating polymer, but it is not very compact, having some porous structures. These are some porous structures. This is the high magnified image. You can see that there are a lot of pores, and these are the sheets of graphene here. So in this case, because there is no additives, the conductivity will be higher, and because there are a lot of pores, so inside the interior of the material can be accessed by the electrolyte ions. So this is the target to achieve. So in these connections, I would like to introduce one of the articles which I did with the Professor Sang-woo Kim in South Korea, in KAIST. So over there, we actually started a technique, is a macroscopic assembly of graphene. So in this case, because the graphene sheets are some micron size, like a 10 micron or less. So the question is that, can we assemble this smaller sheet into larger macroscopic structure? And this macroscopic structure itself is freestanding, and also it retains some pore structure. In this direction, we have introduced some hydrogels of magazine. So the hydrogels of magazine is very similar to, I think you are already familiar with some other regular hydrogels, like some contact lens or some wound healing hydrogels. So in the hydrogel, in those kind of hydrogels, some molecules are interlinked with the water molecule. So major part of this hydrogel structure is made of the water. I mean, water content is more than 90%. So to get similar mimicking structure, we started to assemble the graphene oxides in the form of graphene hydrogel. How it happens? So just let me introduce this one. This is the simplest structure of the cross-sectional structure of the graphene oxide. So this is one graphene oxide, this is another graphene oxide, and there are some surface functional groups, and those surface functional groups have the hydrogen bonding with the water molecules, and they are in a dispersion state. They are the separated individual layers. Now when you reduce it by some chemical form, then what happens, you see that in these regions I have strip off the functional group selectively here and here, because once I strip off the functional group selectively, then what happens, the graphene, they have a strong van der Waals interaction. So as a strong van der Waals interaction, there will be overlapping in this area. However, due to still presence of some residual functional group, they make some hydrogen bonding with water molecule, and this water is stably bonded with this particular framework. This is that I showed you with the two graphene sheets, but instead of two graphene sheets, the million of graphene sheets can be assembled like this. So we have used some zinc plate here, some metal plate, and put it in the graphene oxide solution. Once we put in the graphene oxide solution, then what happens, due to the difference in reduction potential of graphene oxide and zinc, that there is a spontaneous electron transfer from zinc to the graphene oxide. And this electron transfer actually reduces strip of the functional groups from here, and it leads to chemically functionalized graphene. And once this one layer of chemically functionalized graphene happens, then another layer got reduced, and they restack like the way I discussed, but complete restacking is prohibited by this the hydrogen bonded water molecule. So it leads to a structure, porous structures, where water is bonded in between the graphene layers, so that we can get this kind of structure. This is the hydrogel structure. You can imagine that this is a very big structure where we started with the graphene, but the graphenes are of some micron in size in the lateral side. And as you can see from the cross-sectional ACM image, that this is a really highly porous structure. So these are the graphene sheets, and there are lots of pores are available, and it stably bound the water, and the water content is around 87% of its weight, and it has a good conductivity. It has a very high surface area. So as I already emphasized, that these kind of systems which have no binder and is porous structures and very conducting structure, they are good for the supercapacitive performance. So we have tested their energy storage performance with cyclic voltammetry. So cyclic voltammetry is just increasing the voltage from 0 to 1 with some 100 millivolts per second or 500 millivolts per second, 101 volt per second or 2 volt per second. When we do it, then we can get the current, corresponding current. So ideally, this structure should be exactly the rectangular in nature. So any deviation from the rectangular structure is actually signifies that it is not a good capacitor. But here we have charge and discharge at even up to 2 volt per second. Within 1 second, we can go to the 1 volt with 1 volt per second. Just within 1 second, I can charge it to 1 volt only within 1 second, but it's still showing the similar rectangular curve. It signifies that it is a very good capacitive materials because of the presence of the pores, and electrolyte ion can move within these materials, and this is highly conducting. And we checked its areal capacitance. The areal capacitance is more than around 33.8 millifarad per centimeter square, and with the increase of current density, this current density increase means we are charging and discharging at a very faster and faster rate. It's the highest current density, like around 130 milliampere per centimeter square. It leads to the charging of this device with some hundred of milliseconds. Within some millisecond, you can charge it. And this result we have compared with, at that time there are certain the papers which are highly reputed journals. It was published. We compared with them that this capacity is really high. The capacitance and power, energy and power is much higher as compared to those publications. And in this direction, we thought that because although the areal capacitance is high, now the question is that can we increase the areal capacitance to the much higher level, because the areal capacitance was around 33 millifarad per centimeter square. And already we know that these kind of pseudo capacitive materials like polyaniline and polyaniline and magazine, they have a very high pseudo capacitance because of the surface reactions. So can we couple this polyaniline nanofiber with the graphene oxide sheets? So in this case, we use the similar strategy. We just mixed the polyaniline nanofiber with graphene oxides, and this polyaniline nanofiber makes some, because polyaniline also has some the pi structure in its structure. So polyaniline actually can make some pi bonding with this graphene oxide structure. So they remains associated with the graphene, and then they assemble exactly the same way as I discussed. They assemble in the form of some hybrid hydrogen. Here, this process is known as the co-assembly of graphene and polyaniline, known as the PANI. So we got some bigger hydrogel structure, and this, but from the FESM image, as you can see that these thinner sheets, these are the graphene sheets which wrap the polyaniline nanowires, and there are still lot of pores are available. Through these pores, the ion can go inside the materials so that its individual surfaces can be accessed, and its aerial performance you can expect very high. And from the TEM image, you can also see that these thinner sheets, these are of graphene sheets, and these nanowire structures, these are of polyaniline. And as you can see that previously the performance was like 33 millifarad per centimeter square, but right now the aerial capacitance we can increase more than 800 millifarad per centimeter square because of the presence of this polyaniline structure. And in this case, although as you can see that aerial capacitance is around 853 millifarad per centimeter square, and also it retains the performance at a very high charging and discharging rate. Although we have achieved large aerial capacitance, but the gravimetric capacitance, which is the capacitance per unit gram, it remains around 350 farad per gram in this case. Now the question is that, can we increase this gravimetric capacitance, that the per unit gram of the material we can store much of charges? Is it possible? Then we inspected that how to improve, how to increase the gravimetric performance in this case. So we have checked that this is a schematic of the polyaniline nanowire. So all the Faradic reactions happens on the surface. If you go to the bulk core of these nanowires, they are actually effectively unutilized. So although we have used the polyaniline nanowires, but mostly their surface are active, but the core is inactive. So we can remove the core. This is one possibility, or we can downsize this nanowire to a more nanoscopic scale, like some 30 nanometer or 20 nanometer, so that there will be less core structure, mostly surfaces. So to get this, this is one of the reason that one of the way that how to increase the gravimetric capacitance. And another is that if we can make in this case, this is the graphene sheets actually wrapping the polyaniline. There is no direct the atomic level connection in between the polyaniline and graphene. This is kind of physical wrapping. So it is possible if we can downsize the polyaniline to some nanoscopic scale, and also we grow them directly over the graphene surface, there will be a direct connection of this polyaniline with the graphene surface. So how to do that? So in this case, we first check that, okay, we have our hydrogel structure, the graphene hydrogel, and because hydrogel is porous and there are a lot of water trapped in between within the hydrogel structure. So we consider that can we use this hydrogel as a reaction medium, because there are a lot of water trapped in the hydrogel. So this trapped water is actually can be thought of as a microenvironment. Can we make some chemical reaction within the microenvironment? So for that, we gone to the very known method of the aqueous and organic interfacial reaction. So in the aqueous organic interfacial reaction, people used to use to grow some nanomaterials. Instead of using the purely aqueous phase, why people use the organic aqueous phase? Because of the case is that there are two reactants, they are separated in the two different phases. So they cannot immediately mix to form certain nanomaterials. Whereas in the aqueous phase, their mobility and their diffusivity is so large, they can make the reaction immediate. But in the organic and aqueous phase, there are diffusion of these reactants through this interface slowly, and this slow process can give rise to the growth of the uniform nanostructure. So we took this one as a idea. So can we replace this aqueous phase with a hydrogel? Because hydrogel is some kind of membrane within which the water is entrapped. So we remove this aqueous phase and put a hydrogel over here. So once we put a hydrogel, then the reactant has to go passing through the channels of the graphene inside the graphene hydrogel structure. Whenever it diffuses through this, it can interact with the graphene surface, and also the diffusion of those reactants will be much slower even as compared to the aqueous organic phase, because here the diffusion is limited by the interface. On the case of our case, when we use instead of a aqueous phase a hydrogel, the diffusion will be limited by the interaction of these molecules with the graphene also. So we have, this is a schematic image where you can see that each and the individual graphene surfaces are actually covered with the very tiny the polyaniline structure. And here is the FERCM image. So the background is the graphene, over which there you can see that there are spikes in the range of 20 to 50 nanometers. So we can downsize the polyaniline. And also, as you can see that this is another sample with some control that we can also control the dimension also in the lateral dimension of these kind of structures, and they grow over the graphene. There is no bulk phase. But if you, instead of using this particular arrangement where we named it as a hydrogel organic interfacial reaction instead of aqueous organic interfacial reaction, if we use the other way around, instead of graphene hydrogel, if you do react, then it will give rise to this kind of bulky phase. So with this, we have also done the molecular dynamic simulation to check that whether our expectation that during the passage of this the reactants through this hydrogel, there is some interaction of these molecules with the graphene sheets are there or not. Efficient of these the reduces, so this slow feeding of the reactant into the hydrogel gives rise to this uniform structure which we expected and we have found from our molecular dynamic simulations also. And as you can see from the TEM image, that right now in the TEM you cannot see any nanoair structures of the polyaniline, so there are uniform coating of the polyaniline over these graphene sheets, and there is some uniform distribution of the carbon nitrogen, which also signifies that there is a these polyaniline uniformly covered over the surface, and also XRD analysis gives that this particular material is a polyaniline. And as you can see right now, we targeted the specific gravimetric capacitance, as we mentioned that because we have downsized it, and also they are directly coupled with the graphene, we can increase the specific capacitance. We have achieved specific capacitance up to 503 farad per gram. So previously it was around 350 farad per gram, but because of this particular strategy, we can increase the gravimetric capacitance to a large extent. And not only this structure, that I would like to introduce this one also, that using the graphene hydrogel as a reaction media, interfacial reaction media, this is not only limited to the polyaniline, but it can be extended to any of the nanomaterials growth. Like for example, we have tried with the variety of materials. We have tried with the metal organic frameworks, with the copper based metal organic frameworks. You see that whenever we use hydrogel organic interfacial reaction, it gives rise to some nanobelt structure connected with the graphene, whereas in the bulk reaction, when there is no graphene hydrogel, it leads to some random or bigger structures. Similarly, the same is the case for the cobalt based MOF. Whenever we use the graphene hydrogel as a reaction media, we also control the growth and it leads to some uniform and the tiny growth of these nanocrystals. And with this, I would like to move to my next section. It's a magazine-based hydrogel. So in the magazine-based hydrogel, what is the importance of the magazine? Let me again give a review. As I mentioned that this magazine, they are highly conducting. These are the it has a metallic conductivity. This is good for the supercapacitors, and they have a high surface area similar to the graphene. I mean, not similar to the graphene, but they have a high surface area. But they can give the similar effect to the graphene in the sense that they have a good EDLC type, electrical double layer type capacitors, because they have a high surface area. And also due to the presence of these functional groups, those functional groups can give rise to some redox activity, the pseudo activity. So as a result, in this material, we are having both the performance. We can get the EDLC type like graphene, and we can get the pseudo capacitive type like polyaniline within the same material. So that's why this one is very important. And we inspected that can we assemble those magazine exactly the same way as the graphene which we did. We tried that initially. Then we found that whenever this magazine get assembled over the zinc foil to give a hydrogel, that hydrogel is very brittle, and actually it is not forming any freestanding structure. So to make a freestanding structure, we inspected why it is we are not getting the freestanding structure. We thought that this magazine sheets, they are of ceramic in nature as compared to this graphene. This is a polymeric in nature. So this ceramic structure, they have a less seed to seed interaction, and the seeds of the magazines are much lower also, because graphene seeds are like 10 micron, whereas the magazine seeds are like 1 micron. So they have a less interaction. So that's why we cannot make the freestanding magazine hydrogel. So we tried to introduce some little bit of amount of graphene over there, like 5% to 20%. Okay, so lowest one was 5%. So with the 5% of graphene, can we get some freestanding structure made of the magazine and the graphene, where the magazine is the 95%. So we call this as a magazine hydrogel still, but this graphene, the role of graphene is the gelator. They can give the mechanical stability. So we have done exactly the similar strategy, and we have found this structure where it is made of the magazine and the graphene, and you can see that we are getting the porous structure and it's a freestanding structure. And in the TM image, we can see that these seeds, these are of magazine, whereas the background seeds, bigger seeds, these are of graphene. So we have successfully made the magazine and the graphene hybrid hydrogel, where the magazine content is around 95% and the graphene content is around only 5%. And this graphene is actually gives us structural stability mainly, because the most of the property will come from the magazine, because magazine makes the 95% of it. And we change the oxidation state. This is one of the key of that publication, is that whenever people do some assembly of graphene with the magazine or make some processing, they used to use some hydrothermal method, some temperature involved method. But these magazine seeds, they are very susceptible to oxidation. So if someone use some thermal treatment even at just 90 degrees Celsius, you can see that the other peaks like Ti2 plus, 3 plus, and this is 2p, these are of magazine, but here there is a peak, it corresponds to a TiO2. In the pristine magazine, which we started with, it had also some impurity phase like TiO2, but whenever you do it in a hydrogel, like a temperature involved method, so there is an oxidation and TiO2 content increases. This TiO2 is insulating in nature, so as a result, it gives rise to the overall conductivity of the material decreases. But however, in our case, this is the starting material magazine, but when we made it hydrogel, you see that TiO2, the peak of the TiO2 remains very similar. So there is no further oxidation from this processing. So this gelation is an oxidation protected gelation, where we can avoid the oxidation, which is very common any of the thermal processing method. And we got the very good supercapacitive performance. So more than 600 farad per gram, it was some record value for magazine based system, and the mechanism of its high capacitance is like this. This is the magazine. These are the functional group, oxidative functional group. So over here, so the the sulfuric acid medium, this H plus ion can reversibly attached or it can be detached, and as a result of which there will be a reversible change in the ionic state of those titaniums. So as a result, this is another Faradic reaction, and due to this Faradic reaction, it can give rise to the good pseudo capacity. And as a result of its high conductivity and high surface area, it also gives the good electrical double layer type. In combination of these two, we are getting the very good capacity. And we also did another stuff that, I mean, sometimes the requirement is a high volumetric capacity, because when you want to use it for compact space, you have to put it in a compact space. The energy storage devices should be very compact, but this porous structure, there are a lot of water inside, so this volume is large. So we compressed them with some mechanical compression. But during the compression, we did one technique that we first introduced some electrolyte. So whenever we did the compression, so this electrolyte, sulfuric acid electrolyte, actually keep them separated. We cannot make them completely put one upon another. So there is some space is still available. This is due to electrolyte ion, and as a result of this electrolyte protected compression, we got very good performance. And here are some comparison chart, I mean, which shows that our performance, like this volumetric performance, 1522 farad per centimeters cube, is much higher than the most of the previous reports. And not only this 2D hydrogel which I introduced, we have also done the 3D hydrogel, where instead of a zinc plate, we use some zinc powder and let them gel in the form of a 3D hydrogel, and we succeed to make the 3D hydrogel and some casting in the different forms. So it shows that versatility of making the hydrogel according to the any customization. And in next, we targeted that, okay, in the previous case, we knew that there are some, we made the magazine hydrogel, but we needed the graphene to make the gel, because our previous effort to make the freestanding magazine hydrogel was actually goes into vain, because we inspected that why we are not getting the freestanding magazine hydrogel, why we need the graphene. So initially we think that this is the property of the magazine itself. Then we tried a different thing to make the additive free magazine hydrogel. We inspected that for seed-like 2D materials, the van der Waals force goes like this, L by d to the power 9/2. So if we can increase the seed size, so we can increase the seed to seed interaction, and if we can decrease the distance between the two seeds, then we can also increase their seed-seed interaction, so that it is expected that we can make some freestanding structure of the magazine hydrogel. So in this case, first we made the larger size of magazine, and this is a smaller size of magazine. We first did two different type of magazine seeds, and then we increased the dispersion concentration up to like 40 milligram per ml or 60 milligram per ml. And in a high concentration, we have checked this with the polarization microscope, and we have found that there is a spontaneous ordering. There are some domains, this kind of bright domains. These bright domains actually significant that those seeds are not random. There are certain domains, there are spontaneous ordering. This spontaneous ordering is known as the liquid crystal ordering. This is the fact for any of the anisotropic materials. When the dispersion concentration goes above a critical concentration, they show some spontaneous ordering. So if we can make some kind of spontaneous ordering in the solution, we thought that if we put some zinc foil, they will assemble in a more ordered fashion, and with the higher interaction because of this increased L and lesser D. So with the expectation, as you can find that whenever the concentration is below certain critical concentration, we are not getting any freestanding hydrogel. So these are brittle, but whenever we go to the above certain critical concentration, we are getting some freestanding hydrogel. So this critical concentration is size dependent. We have found that for the larger size magazine seeds, it is above 40 mg per ml, we can get the freestanding hydrogel, and for smaller seed, we have to go to the above 60 mg per ml. Then only we can get the freestanding hydrogen. And we have also checked the diffusion of the ions within this hydrogel structure. And this is the bigger seed and this is the smaller seeds. So ion can move like this path. So smaller seed ion can move very easily, whereas in the larger seed ion has to move through this larger path. And as a result, you can see that in the smaller seeds, this shaded contribution gives that how much of contribution is there from the this term is the surface capacitive term, that how these ion surfaces are getting accessed and they are giving the contribution in the capacitance, whereas this term is due to the diffusion of ions. This is known as the diffusion limited. Now we have found that this shaded region shows that the 96% is the capacitive limited, this surface limited. That means most of the surfaces are getting accessed within this freestanding hydrogel structure, either in the smaller seed size or the bigger seed size. This indicates that the hydrogel structure has a very good porosity, and the continuous porosity leads to accessibility of the ions to the individual seeds, and this leads to the good capacitance also. And this is some comparison chart with the some previous literatures. And finally, this one is the case. It is also a kind of magazine hydrogel structure, but here our target was different. Target was we started this work with the two target. One is that the critical concentration required for this freestanding hydrogel was so high, like 50 mg per ml or 60 mg per ml. This is hard to achieve, this high concentration. Can we reduce the required concentration, critical concentration, to some sufficient level, like 10 mg per ml or 15 mg per ml? This is one target. And another target was, can we control the orientation of the seeds, either horizontal direction and the vertical direction? So orientation control of the hydrogel is one of the focus for this case. So in this case, we use some electric field assisted technique. We use there are two electrodes, we use the voltage. So there is some electrophoretic drag. So the magazine seeds which are of negative charges, it goes towards the positive plate. Here, this is the electrophoretic drag. But simultaneously at this anode, the zinc goes to the zinc plus and to E minus. And these zinc plus ions actually attract those negative charges, negatively charged magazines, and this zinc ion linked with each and every magazine seeds as a linker. So it leads to the oriented hydrogel, and we can get the hydrogel with like this. This is the potential. With the 1 volt potential, we can get a freestanding structure. Without potential is a completely brittle. We use the 10 mg per ml solution, much lower concentration, and as you can see that gelation rate is so high, because in this case within 60 seconds we can get a sufficient thick gel, but if you do not use the voltage, even you cannot get any gel, just a slight deposition over there. And we can control the orientation of the magazine seeds, like parallel orientation. So you control the orientation of the field. If you use positive and negative like this parallel configuration, you can get this kind of seeds. When you use the coaxial assembly, centrally there is a zinc wire and there is another coaxial cable kind of thing. This is made of also zinc. So the electric field distribution is radial over here. So as a result, there will be a radial distribution of the magazines, and you can get a monolithic structure where there is a vertical arrangement of the seeds like this. This is a horizontal arrangement. You can see that the seeds are horizontal, and whereas in the case, if you check from the top of this monolith structure, you can get that arrangement is also parallel. So they are vertically arranged like this, which is also confirmed from the FESEM image. And they give the excellent energy storage performance. So we have used mainly for energy storage performance, and the vertical one we used for the evaporation and the evaporation of the salty water, which I am not going to introduce over here. Only just I am focusing on the energy storage performance. So we got the very good energy storage performance, and this vertical structure of this impedance curve, this is the imaginary axis and this is the real axis. Whenever it is going parallel to the imaginary axis, that means it is the capacitive in nature. There is less contribution of resistive part, and this highly capacitive nature also is coming from the easy facile diffusion of ions within these porous structures. And let me introduce my teams. So here is the work I have presented, mainly done by Anirban and Pranoy. So it's their work, and I would like to also introduce my team members and collaborators. So Professor Sang Kim of KAIS, he was my mentor during my postdoc, and still we are in touch and we are doing some collaborative works. Professor Subhradeep Ghosh from our own department, Anki Reddy, already he left IIT Guwahati, and he joined IIT, I think, Andhra, I guess, and Dr. N. Padma from BRC. Thank you for your attendance and attention.
Thank you, sir, for your inspiring talk. Now we'll begin the question answer session for this topic.
Hello?
Sir, Mr. Dinesh is asking, how do we find the best voltage window from the cyclic voltogram? How do we find the voltage window theoretically?
Okay, that's a very good question. So the thing is that it's a very good question. Let me go to the one of the CV curve. So we go to the one of the CV. Oh, okay. Okay. Yeah. So you see that here I have used the 1 volt window from 0 to 1 volt because I have used the aqueous electrolyte. So aqueous electrolyte, water generally dissociate. The dissociation energy, which if you convert to the voltage, that is 1.23 volt. So if you use 1.23 volt, water will dissociate. So you don't want the dissociation of the electrolyte. So you have to be within the limit of its dissociation potential. So in this case, I have used up to 1 volt, although theoretically I can go to up to 1.23 volt. But what happens, because I have used the graphene, so at above certain voltage, graphene also can catalyze and it can give rise to the some oxygen evolution or hydrogen evolution. So to be in the safer side, we have choose up to the 1 volt, not up to the 1.23 volt. 1.23 volt is the theoretical limit. We kept below that because you have to check the catalytic activity also. Whether reaching to 1.23 volt, we are getting some huge increase of current here or here. If we are getting some huge increase of current, that is not due to the some storage of the ions, that is basically due to the some catalytic activity. Now, if you want to go beyond just 1 volt, go to like 2 volt or 3 volt, you have to use some other electrolytes, not the aqueous based electrolytes. You can use the organic electrolytes, over which its stability is much higher. You can go to the some 2 volt or 3 volt, or you can, if you want to go much higher than that, even 4 volt, you can use the ionic liquid electrolyte, which are having the higher potential, but the difficulty with those electrolytes is that they are viscous in nature. So the ionic movement within those viscous electrolyte is less. Although you can increase with those, let me, yeah. So you see that capacitance E is equal to half CV square. So although you can, the V you can increase, because the potential, it is a square of V. So if you can increase the potential window, it is always better to get the higher energy density. But at the same time, because of the high viscosity, there will be the diffusion of the ions will be less. So as a result, the capacitance decreases to a great extent. So I mean, the advantage of the using the other electrolyte may not be always useful. But if you want to go to the much like higher energy density with a slow charging discharging, then you can definitely use the other electrolytes with the higher voltage window.
Thank you, sir. The next question is from Deen Dayal Dubey. What type of dielectric can be used in this pseudo capacitor and EDLC?
You see that, let me show you the in this case, it's a dielectric capacitor, but when we talked about the electrical double layer capacitor and pseudo capacitor, there is no such physical dielectric material. Okay, so this dielectric material which we intentionally incorporate, these are the case of the dielectric capacitor. In this dielectric capacitor, their capacitance is very less. But for double layer capacitor, so here the dielectric is the water molecule. You see that it's a positive charge, negative charge separated by the water molecule. So the separation here, the separation is the D is the separation. Separation is with the some physical dielectric, but here the separation with the water molecule. So water molecule serves as the dielectric here. The same thing also the case here. The water molecule serves as the dielectric. But if you want to, there is no physical dielectric we are using, suppose like which used to use in the some electronic industry. These are not kind of dielectric. Here the dielectric is the electrolyte molecule. So if you use, instead of water, if you use the organic electrolytes or ionic electrolytes, in that case the these molecules will be replaced by the some organic molecules. That's all.
Thank you, sir. The next question is from Dinesh, Mr. Dinesh. Can we perform cyclic stability test at high current density like 10 ampere or more to reduce the time involvement? Will it affect the performance of the supercapacitor?
Yeah, that's a good question actually. So definitely we can do it at higher current density. But if you do it higher current density, you need to consider that like these materials, like graphene based materials. So graphene based materials, they are very stable. For EDLC material, definitely we can do the stability test at higher current. There is no issue. But if we use any pseudo capacitance, and if we do the cyclic stability test, cyclic stability means we are charging and discharging. So we need to consider that what is the stability of this material at a higher current density. Okay, so if you use like polyaniline, if you use the polyaniline, so polyaniline, if you start charging and discharging at a very faster rate, so what is going to happen during the charging, it actually swells, and discharging it actually again contracts. So there will be a swelling and deswelling. As a result, if it happens at a very faster rate, then it can disintegrate. So the stability of the material is the issue. So if the material stability is very high, definitely you do the stability test at a higher current density, but you need to consider whether during this charging and discharging method there is any physical problem is there. I mean the material stability is there or not in the system.
Thank you, sir. The next question is from Dr. Biju. Which pseudocapacitance is more crucial in the pseudocapacitor? Intercalation pseudocapacitance or the surface redox pseudocapacitance?
Yeah, so the intercalation type, I mean, both are important, the intercalation type and the pseudocapacitor type. But the thing is that in the intercalation type, so intercalation type, it mostly actually limited to the surfaces, because intercalation is in between the two layers. Some ions